Hello there. In this video, we'll be dealing with examples on one-sided limits involving the radical function. But first, recall that one-sided limits is a type of limit that is only concerned with the behavior of f as x approaches a from either the left or right side. Let's have this graph as an illustration. As x approaches a from the left, the value of f of x is represented by this limit here. Similarly, as x approaches a from the right, the value of f of x is represented by this limit out here. Now that this is out of the way, let's dive into a little bit on radical functions. So radical functions are functions of the form this one out here, wherein we know that there are two cases for n. Either it is odd or it is even. So let's start with the odd case. In limits, when we have n to be odd, then we'll simply directly substitute the given value of x. Since we know that if n is odd, the domain of this function inside is all real numbers, or are all real numbers. However, if n is even, we'll have a little bit of problem. Let's have this illustration. So we have here the function square root of x with the graph shown here. And let's try to focus on the value at x equals 0. At x equals 0, notice that the limit actually does not exist, since it doesn't have a limit from the left, or that is, the limit of f of x as x approaches 0 from the left does not exist. Clearly, there isn't any function approaching this one out here. And why is that? Well, take note that the domain of the function is given by 0 up to infinity. This is the case since we know that with radicals that has an even index, this expression out here must be non-negative. So its lowest value is only 0. So we'll have problems with value from the left or left of 0 or the negative values out here. So that is something that we need to take note when dealing with the limits of radical functions. So in this video, our focus are on examples with radical functions that has an even index. So let's start with our first example. In here, we are tasked to find the limit of square root of x minus 1 as x approaches 1. Before we start, feel free to pause the video so that you can try this one first on your own. Okay, so let's start. So initially, what we might think is we want to directly substitute 1 into this function, or that is, we'll have this to be square root of 1 minus 1 or 0. However, again, this is a radical function with an even index. So again, if it is not shown out here, it is immediately assumed that the index is 2. But that is actually not the case out here, since you'll see later that the limit of square root of x minus 1 as x approaches 1 is not actually 0. And again, the reason behind this is because the domain of this radical function runs from 1 to infinity. So this was obtained based on the expression inside. So let's clear out some space. So to solve this one, let's try to use one-sided limits. So let's start with the one-sided limit from the right of 1. So let's try to inspect this one. Observe that if we plug this value in this radical function, we'll have this one. And we denote this symbol out here as values from the right of 1, or values greater than 1. So when we deal with values greater than 1, these are values such as 1.001, 1.0001, and so on, such as, no matter how many zeros that is, that are close to 1. So given this, what happens when we subtract this by 1? So we're trying to illustrate this idea out here. Then we know that the value would be something very close to 0. Something very close to 0. Something like that. But the important thing to note here is that when we subtract these two, the outcome is positive, since this value out here is greater than this one out here. So the outcome for this one is 0, or from the right of 0. Sorry about that. So these are values from the right of 0, or this one out here refers to approaching 0 through positive values. So that means that since these are values approaching 0 but positive, then we know that this radical out here exists and its outcome is 0. So therefore, we can conclude that the limit of this radical function as x approaches 1 from the right is 0. So this limit, this one-sided limit out here, is similar to what we had a while ago when we just plugged in 1 minus 1 out here. But the crucial case is the next one. Let's deal with the limit of square root of x minus 1 as x approaches 1 from the left. So let's inspect this one. So upon plugging this in, we'll have this one out here. And again, this one out here refers to values from the left of 1, or values less than 1. So these are values close to 1 but less than it. So this may be like 0.99999 and so on, minus 1. So we're trying to illustrate this one out. So what happens when we subtract this? Well, we'll have a value that is negative. We'll have a negative value out here since this one is less than 1 out here. So we know that their outcome when subtracted is negative. So we'll have here 0 from the left, or this refers to approaching 0 through negative values. Or what this means that the values out here are like 0.00001, that is negative, something like that. And so given that, we know that the expression inside the radical is negative. No matter how close it is to 0, it's still negative. Therefore, this radical out here is undefined. And so we conclude that this limit, this one-sided limit, is equal to does not exist. So this limit out here does not exist. And so since these two limits out here are not equal, and in fact the other limit does not exist, we conclude that this limit out here does not exist. So that is how we can get the limit of a radical function that has an even index. We can use the concept of one-sided limits to obtain. Now, before we move on to the next example, let's take note of this remark. So in the last video, we learned that if the limit from the left is not equal to the limit from the right, then the limit as x, or rather the limit of f of x as x approaches a, does not exist. Actually, the same is true if the two one-sided limits are equal. Let's say if this two are equal to L, then we can conclude that the limit of f of x as x approaches a is equal to L. So this is a remark that we need to take note in order to answer the next example. So let's go on to the next example. In here, feel free to pause the video so that you may try this one first on your own if you have an idea on how to answer this one. Okay, so let's start. Again, we'll try to use the concept of one-sided limits outing, starting with the limit of f of x as x approaches 1 from the left. So when we are dealing with these values, so we refer to values less than 1. So we'll use this function out here. So let's try to inspect what happens when we plug this value in this expression. So we'll have here this one out here, and again, we'll have here 1 minus values from the left of 1 or less than 1 that is close to it. So that's like 0.99999. So regardless of what value this is, we know that the outcome is positive. So therefore, we have here 0 with a positive sign, or these are the values approaching 0 from the positive side or the right side. So therefore, we know that this radical is equal to 0. So we conclude that this one-sided limit is equal to 0. Let's go on to the other side, the limit of f of x as x approaches 1 from the right. In here, when we talk about 1 from the right, we talk about the values of x greater than 1 but close to it. So we'll use this function out here. So we have here this one, and since this is just a polynomial, we can use the trick that we learned in a previous video, that when dealing with polynomial functions, since its domain is all real numbers, we can simply plug in immediately 1 out here. So we have 1 squared plus 1 minus 2, or when simplified, this is equal to 0. Therefore, this one-sided limit is equal to 0. Since these two are equal, we conclude that the limit of f of x as x approaches 1 is equal to 0 by our remark earlier. So that is the answer for this problem. Let's go on to our last example. Again, feel free to pause the video so that you may try this one first on your own. Okay, so let's start. So in here, we are tasked to find the limit of g of x as x approaches 2. And we are given this g of x out here. First, to solve this, take note that we can factor out this expression into x minus 2 times x minus 3. So we did that since we'll be needing this factored form later in analyzing the one-sided limits of this one. So now let's start. So let's start with the limit of g of x as x approaches 2 from the left. So we just replaced g of x out here with the given radical function, and let's now try to inspect what happens when we plug in this value into this radical function. So upon plugging it in, we'll have this, and let's try to inspect this one. Observe here that for this one out here, we'll have 2 from the left, so that our values are like 1.9999 minus 2. We know that this outcome is negative. So we'll have here 0 from the left. For this one, we have 2 minus 3. Note that we can simply remove the negative sign out here since the outcome for this one will be negative 1. And note that we can remove the negative sign in 2 since negative 1 is a fixed value. Or what I mean by that is that it has a fixed sign. We know that it is negative. Even the values close to it from the right or the left is still negative. So we just consider this one. No need to put signs out here. So given that, we'll have this one out here, and take note of this one. This is important. In here, we have a negative value. And we also know that the values from the left of 0 or less than 0 are negative. So when we multiply these two, the outcome is positive. Therefore, this is equal to 0 from, or approaching 0 from the positive values, or 0 from the right. Approaching 0 from the right, there. So take note of this one, since this means that we have a value for this radical, and that is 0. And so we conclude that the limit for this one-sided limit out here is equal to 0. So as you can see, it is really important that we know the factored form out here. So let's move on to the other one-sided limit, the limit of g of x as x approaches 2 from the right. So let's just replace g of x with the given radical function, and let's try to inspect this time. So what we'll do is we'll plug in this into this radical function to obtain this one out here, and from here let's try to inspect. Again, for this value, since it won't approach 0 in any case, we'll just have 2 minus 3, and that will be negative 1. For this one, let's try to focus out here. From the right of 2, those are values such as 2.000001 minus 2. Then we know that no matter how close this is to 2, the outcome is positive. So we have in here this. So we have values from the right of 0 and negative 1. And take note of this. So we have here a negative value. And we have here, from the right of 0, those are positive. So when we multiply these two, the outcome is negative. So therefore, we have in here 0 from the left side of 0. Since we know that this refers to approaching 0 from the negative values, we know that the expression inside is negative. And again, in radicals, we can't have a negative expression inside it. Therefore, the outcome for this one is undefined. So we conclude that this limit out here does not exist. And since these two limits are not equal, and in fact, this limit even does not exist, we conclude that the answer for this problem is does not exist. So the limit of g of x as x approaches 2 does not exist. And so those are our examples on dealing with the limits of radical functions. To formally end this, here's an exercise that you may work on. So from here, we have a piecewise function with two radicals in it. So the idea to solve this one is similar to the second example, along with the third example, since we have this. So your goal here is to find the limit of h of x as x approaches 3. So does the limit exist or does it not? Comment down below if you have an answer to this one, and even feel free to share if you have a solution out here. So that's it. I hope you enjoyed and learned a lot from this one. So yeah, that's all for this video.